Hello and welcome to problem set 29. Our problems today will be from the topic lipid metabolism and fatty acid oxidation. Before we get started, just a quick reminder that the worksheet to accompany this video is available online through my website. And with that said, let's get started with number one. There's actually only one problem today, but it has an A through E, so it's a multi-step problem. Okay, refer to the fatty acid spiral and the Krebs cycle as needed to complete A through E. Palmitic acid is a saturated fatty acid with 16 carbons in its chain. A, how many turns in the fatty acid spiral does it take to oxidize one molecule of palmitic acid? Okay, so A. Just asking how many turns in the fatty acid spiral it's going to take for palmitic acid. So we're going to break down palmitic acid in the fatty acid spiral into the 2-carbon acetyl portion of acetyl coenzyme A. So take your 16 carbons, because we're told that palmitic acid has 16 carbons, divide it by 2, and that's going to tell you the number of acetyl coenzyme A's you're going to make. You're going to make 8 acetyl coenzyme A's. But remember that the last turn of the fatty acid spiral is going to make 2 of those at the same time. That means you always have 1 fewer turn than the number of acetyl coenzyme A's that you make. So we're going to get 7 turns. That's the answer to part A. Part B. How many acetyl coenzyme A molecules form from one molecule of palmitic acid? So we actually already answered that question. It's going to be 16 divided by 2. We're going to get a total of 8 acetyl coenzyme A molecules from the breakdown of palmitic acid. All right, part C. How many reduced coenzymes of NADH and FADH2 are formed from fatty acid oxidation of one palmitic acid molecule? Okay, so we know, and you can look at the fatty acid spiral if you need to, we know that for every turn in the spiral, we're going to get 1 NADHH plus and 1 reduced coenzyme of FADH2. Okay, but that's per turn in the fatty acid spiral. How many turns do we get for palmitic acid? We get 7. So that means that we're going to get a total of 7 NADH H plus and 7 FADH2 total, because we have 7 turns, and each turn is going to give us 1 each of those reduced coenzymes. All right, part D, let's go ahead and erase before we do part D and E. Okay, part D. How many ATP would result strictly from the fatty acid oxidation of one molecule of palmitic acid? So our previous answers will be helpful here. Remember that we're going to get 16 divided by 2, or 8 acetyl coenzyme A's, which means 7 turns in the fatty acid spiral or fatty acid oxidation. And then remember, from each turn we're going to get 1 NADH H plus, 1 reduced coenzyme of NADH, and 1 reduced coenzyme of FADH2. And when those get reoxidized later on, remember I do the curly Q to represent later on that that's going to happen in the electron transport chain, It's going to power the synthesis of ATP from ADP in oxidative phosphorylation. And we get 3 ATPs for every reduced coenzyme of NADH. So plus 3 ATP. And we're going to get 2 max yield, that is, for every reduced coenzyme of FADH2 that's getting reoxidized. So plus 2 ATP. That's a total of 5 ATP, and that's for every turn you get in the spiral. Okay, but how many turns do we get? We're going to get 7. So we know that we're going to need to times that number by 7. 7 times 5, we're going to get 35 ATP from fatty acid oxidation. However, do not forget, it's always going to take 2 ATP to activate the fatty acid so that it can be oxidized in fatty acid oxidation. So minus 2 ATP to activate the fatty acid. That leaves us at plus 33 ATP, and that is our answer for D. Okay, let's go on to part E, and although this answer will be helpful for part E, we're going to need a lot more room. Let's see how much we can do right over here. Okay, part E. How many ATP will result from complete catabolism of one molecule of palmitic acid? All right, so we're talking about complete catabolism. We're talking about the 16-carbon palmitic acid being broken down into our 8 acetyl coenzyme A's, and that happens in fatty acid oxidation. And then those acetyl coenzyme A's in complete catabolism would enter the Krebs cycle for full conversion into carbon dioxide. That also gives us a guanosine triphosphate for each turn in the Krebs cycle. And because we're oxidizing, the coenzymes get reduced. 3 coenzymes of NADH, H+, and 1 FAD, H2, which will be then reoxidized in the electron transport chain, powering oxidative phosphorylation, or the phosphorylation of ADP into ATP. They get reoxidized into NAD+ and FAD by ultimately passing their electrons and hydrogen ions to oxygen from the air that we breathe to make water. The energy from that exergonic process is used to phosphorylate ADP into ATP, oxidative phosphorylation. All right, so we already accounted for the energy required, the energy generated from the breakdown of the palmitic acid into the 8 acetyl coenzyme A's. We said that's going to take 7 turns in the fatty acid spiral, and it's going to give us 33 ATP. So we already did this part, but now we've got the 8 acetyl coenzyme A's. We have to account for the energy to break those all the way down into carbon dioxide in the Krebs cycle, getting those reduced coenzymes that are going to be fed into the electron transport chain and power the synthesis of more ATP from ADP. Okay, so we've already got part of this done because we already did this in part D. So let's do the rest, and let's take our 8 acetyl coenzyme A's and figure out how much ATP we can get from that in the remaining processes. Remember, from the Krebs cycle, we get 3 reduced coenzymes of NADH and 1 FADH2 for every turn. We also get 1 high energy molecule of GTP. Later on, when those reduced coenzymes are reoxidized, remember that we get 3 ATP per NADH that's reoxidized. So 3 times 3, we get 9 ATP. And we get 2 ATP for every FADH2 that's reoxidized. So times 2, because remember FADH2 enters the electron transport chain at a later point, therefore giving us less energy and synthesizing less ATP. So here we're going to do 2 times 2, so 2 ATP. And remember, we're going to count our GTP as an ATP. And that's how we come up with, always the same number here, 12 ATP per turn in the Krebs cycle. Okay, that's for the Krebs cycle. Now, how many turns are we going to get in the Krebs cycle? 8, because we're going to get 1 turn for every acetyl coenzyme A that enters it. So we're going to do 12 times 8 plus 96 ATP from the Krebs cycle. Now don't forget, from the tutorial, we need to add these 2 numbers together. So I'm going to just remind you of where those 2 numbers came from and why we need to add them together. Remember that the 33 ATP was accounting for the ATP that we're going to get when the reduced coenzymes from fatty acid oxidation are reoxidized in the electron transport chain and powering oxidative phosphorylation, that is making ATP from ADP. So how much ATP are we going to get from that process? 33 ATP. Don't forget the -2 to activate the fatty acid for the fatty acid spiral. The 96 ATP is coming from our 8 acetyl coenzyme A molecules that are going to be completely oxidized to carbon dioxide and water, and the energy produced is going to be used to synthesize more ATP. How much more? 96 ATP per molecule. All right, so let's add those numbers together, 96 and 33. And we get our final answer, which is 129 ATP. I'm going to circle that also with this pink pen because that is our final answer. Okay, so this will conclude our problem set 29. I hope that you will consider tuning in to tutorial number 30. Thank you very much.